Given a modulus n and a with the greatest common divisor of a and n equal to 1, the least power k for which a to power k is congruent to 1 mod n is the order of a. We're guaranteed that a to the phi of n is always congruent to 1, but it's possible that the order is a divisor of phi of n. If the order is actually phi of n, we say that a is primitive. We've found primitive roots exist for all prime moduli, so what if n is composite? For example, if n equals 35, then phi of n is... So the orders of an element mod n could be... So proceeding as before, we want to find an element of order 2 cubed and an element of order 3. To find an element of order 2 cubed, we'd want to eliminate all elements of order. All roots with these orders solve x to the 12th congruent to 1 mod 35, and Lagrange's theorem tells us absolutely nothing because 35 isn't prime. However, we can still use the Chinese remainder theorem and split the factors of the moduli. If x to the 12th is congruent to 1 mod 35, then x to the 12th is congruent to 1 mod 5, and x to the 12th is congruent to 1 mod 7. So we can solve x to the 12th congruent to 1 mod 5 by noting that since phi of 5 is 4, then x to the 4th is congruent to 1. And that means we can reduce this power down to an identity. So this is going to be true for all values of x, which means our solutions will be found from x to the 12th congruent to 1 mod 7. So phi of 7 is 6, so again, x to the 6th is congruent to 1 mod 7, and so this congruence reduces down to another identity. We started with n as a product of distinct primes, where phi of n is going to be p minus 1 times q minus 1. We then tried to solve a congruence of the form x to the n congruent to 1 mod p, where n is a divisor of phi of n that omits some of the prime factors. But it turned out that p minus 1 divided n, so all of these congruences reduced to the identity. Was this just a coincidence? Well, let's try it. Let's try 33 3 times 11. So phi of 33 is, and possible orders include, to find an element of order 4, we'll omit one factor of 2 from 20 to leave 10 and solve x to the 10th congruent to 1 mod 33. And we'll split our modulus, and we find and it looks like we've run into another identity. Now, we haven't proven that this always happens, but it doesn't seem very promising, so let's try a different approach. So we know that a to the phi of n is always going to be congruent to 1 mod n for all a with the greatest common divisor of a and n. Now, if n is odd, then phi of n is guaranteed to be even, and so phi of n divided by 2 could be the order of a. So let's check it out. Suppose n equals pq is odd, where our greatest common divisor of our two factors is 1. Then phi of n will just be phi of p times phi of q. And let's consider a, where the greatest common divisor of a and n is 1. So if the order of a is this product, we're done. If the order of a isn't this product, what could it be? If n is odd, both of these must be even as well. So a could have order product over 2. So let's consider that value, x congruent to a to power product over 2 mod n. So again, by the Chinese remainder theorem, we can split the modulus to p and q, and we can do some rearranging of the factors of the exponent. And notice that here we have a to the power phi of p mod p, so that's going to be 1. While here, if we rearrange the factors in a different way, we have a to the power phi of q mod q, and again that'll be 1. And a Chinese remainder theorem says that we have a unique solution mod n, but the obvious unique solution is just 1. Now, because our proof used phi of p and phi of q, we didn't actually rely on p and q being prime. So our theorem holds for many more things besides odd numbers. Let n be p times q be an odd number, where the greatest common divisor of the two factors is 1. If the greatest common divisor of a and n is also 1, then a to the power phi of p, phi of q divided by 2 is congruent to 1 mod n, and so a has order at most product divided by 2. So the highest order any element can be mod 33 is going to be 10. In fact, we get the same result for any divisor d, provided that both phi of pd and phi of q divided by d are whole numbers. And this means our theorem is actually even more general. Let n be an odd product, where our greatest common divisor of the two factors is 1. If the greatest common divisor of a and n is 1, and the greatest common divisor of phi of p and phi of q is d, then any a, has order at most product divided by d. So let's consider the highest possible order of an element mod 247. So 247 is 13 times 19, and phi of 13 is 12, phi of 19 is 18, and the greatest common divisor is 6, so the highest possible order is the product divided by 6. And just as a note, this is the least common multiple of our two phi values. And once more, if n equals pq is an odd, well, you know the rest of it. But phi of n is phi of p times phi of q. So since the greatest possible order is product divided by 2, and that's phi of pq divided by 2, that's strictly less than phi of pq, which means we can't have a primitive element mod product. And so if n is an odd composite number with at least 2 distinct prime factors, there could be no primitive element mod n. Assuming n is a product where the greatest common divisor of the two factors is 1. So what about primitive roots mod p to the n, where p is an odd prime? For that, we'll have to develop some more tools. We'll take a look at that later.